So okay, let me continue with here. Let's try some other filter. So let me first add some noise there, so make it more interesting. So I cannot see anything here. Yeah, let me add some salt and pepper noise. Okay, this is one thing that I very easily make mistake because I'm really a MATLAB guy. When you're using a Python, for example, I write an image, new image is equal to image, stuff like that, and I try to make any changes with, be careful, like this is like a pointer in like C or something like that. If you make changes on this image, this image will also change as well. See what I mean? Like if you are used to MATLAB, you won't think this way. You think, oh, okay, I have new variables, an image here. If I make for example, let me make some changes here. Like an image is equal to, let's see. Well, let me look at the shape of this thing first. Shape is like this, right? 512 by 512. Let me set some of the things to be 0. Let's say the first half of that is not half of it. What? Like half of that is 0. 0 to 255 is equal to 0. And then I image show that. Don't image show that. But okay, image show that anyway. So I set the first half to be 0. It's nothing special like I'm doing, nothing spectacular. But what I just mentioned is that like if you check what's going on with image, so it also got changes because like an image, when you say an image is an image, essentially it's like a pointer. So you make any modification for an image, the original image will be changed as well. So this behavior is very different from what you're expecting if you're used to MATLAB. So so instead, like for example, if let me read this again. So I read the image again. Okay, let's remove this filtering command here. I don't want to filter this. Here. What's going on? Oh, sorry. MATLAB guy. So if I really want to make a new copy, I need to explicitly do that. So I need to say an image is making a copy of that. So if I do that, then like you see the okay, like then the image doesn't change, even though I changed the new image. So let me make a copy of this original image, and let me add some noise there. So let's see. Let me add some so-called like salt and pepper noise, or maybe just pepper noise because I only add kind of dark pixel everywhere. So I can write something like I just type it before I explain it. And start an image. Dot shape is equal bigger than 0.2 with 0. So what I'm doing is okay. First of all, like this command is very much like commands in MATLAB will be just one RANDN. So it's have a normalized Gaussian random variables. With size, the size is equal to the shape of like an image. So my an image shape is I have here is like 512 by 512, right? You see that I have a star here. The star here is like a little bit like I don't know how to call it. It's like a dereferencing something similar in C or something like it. Because when I just put in this thing into that, I have a bracket here, right? But basically, like the argument, I mean this function like rand n expect two arguments there. Expect like the length and the width. So I need to have a dereferencing like command there. I put a star there, which just basically remove that bracket there. So it would behave like, basically it would behave like just np dot random dot out and the and 512 by 512, something like that. So if I don't have this star, then I will have something like this, and it will give me an error message, because it is not it's expecting like two integers instead of expecting a tuple. So this is something. So and then like my command basically saying, okay, generate random Gaussian with size 512 by 512, and then I see like which of those is bigger than 2. So it's like a normal distribution with like mean 0 and variance is just equal to 1, right? So there would be, how many of them? I forgot. 5% more than that. I think like, anyone remember the Gaussian distribution? This is
a third?
third. So I'm saying like, when I'm in high school, I remember those numbers. Now I don't remember. Like it's either 7%. Oh yeah, I trust you. You probably yeah. I think it's like 7%. So it'll be like basically saying like 7% of them I would just set to 0. So I assume I didn't run this command. So maybe I can run this again. I hope it's okay, because every time I just get a new copy here. So I can just show this. Let me show this. Remove this as well. So just show this. So you can see like I have some dot there. Maybe I make it again a little bit bigger. So you see this black dot, about 7% of them basically like use random say that's black. So for this kind of noise, you know that like, okay, what filter is good for this kind of noise? Still remember? Yes, medium, yes. So but we can try different filters anyway. So let's see. I can maybe like I have this an image. Okay, let me just make it every time run it again, because it's so fast anyway. Let me just add a filtering command here. So I would say an image is equal to CV2. Let's try a mean. This is a Gaussian filter, basically. It's like a mean filter, so a Gaussian filter. I can even try a box filter. Right? I have a box filter earlier. Let's try the box filter also. I have the box filter, basically this one, right? 5 by 5 kernels. So this is after the box filter. So it kind of just blur a little bit. It looks still pretty much lots of artifact. So let's compare with like, let's say, Gaussian filter. Oh, shoot. I make changes with image also earlier. Let me try to rerun this. Let's see. Gaussian filter. So that's a Gaussian blur command, basically it's Gaussian filter. And I can set the kernel size here. It's 5 by 5. 2, I think, is the variance. I forgot it's variance or standard deviation. Probably a standard deviation. And yeah, I think that's it. So this is with a Gaussian filter. It looks a little bit better. Of course, it's still not good. Can also try a medium filter. So against this 5 here is the kernel size. So basically it's taking a 25 by 5 by 5, 25 pixel and take the median. And you see like if you, for this kind of noise, median filter is perfect, basically. let's see. Of course, I can add. Let's try to add some other types of noise. Instead of like I have an image is like this, maybe I can have this new image is basically just equal to or I can just say new image is equal to the image at a Gaussian noise. Maybe times 10, I don't know. So it looks like I have some problem. I think it's like the problem is, so what do you think is the problem? Could be, yeah.
Trying to call the shape of an image while you're creating it.
Let's see. Oh yeah, that could be. Let's see. But it looks like no, I already have that. But I can do this. But I think, yeah. So so why? Can you guess? Oh, sorry. Actually, I just realized the size is so small. I'm really expecting you guys have a super good eyesight.
I think the kernel size should be a matrix.
Actually, like here, like it doesn't really complain about this line here, right? So the problem is at this line, right? It's saying the error is really oops, it's so difficult to yeah, it's complaining here, right?
It says that on the second input we should have a matrix, or at least should be a matrix.
This one should be a matrix. This one?
Yeah, it should be in square brackets.
But okay. But just now it was okay. Right? I'm not so sure about it. Like let's do this. Right? Just now it doesn't. Yeah.
Is the image in RGB? Has 2 dimensions?
It's still in. It's in grayscale. It's still in grayscale. But again, another things. If you are used to MATLAB, like me, be very careful with the format because Python is very sensitive, right? Whether you're doing integers or doing stuff like that. Well, most likely, it's like this is expecting like something like maybe let me check the original type of this thing. So let's just go here. I forgot. Is that's a okay? I'm not even sure. Is that a type command here? NDLA. Oh shit! I need to think about it. What's that command to get the D type? Is that?
mg.dtype.
Oh, let's see. Yeah, it has a D type here. So this original is unsigned integer. So here, I put it here. Basically, it is kind of expecting. It make it like not integer anymore. So I can try like and actually let me run this first and let me do this again. Sorry. Yeah, this command actually like this give me something as I fold 64. So probably like if I change it back to integer, how do you do that? I think it's probably I can do it that way. Yeah, that works. So I'm also using medium filter. Just look at like without filtering. Let's see the result first. This is I'm just adding some Gaussian noise here. So as you can see, like just now, I have some problem because when I add a noise that is a different type, basically I add a numpy that by default is basically is a float variable, and then the whole thing becomes a float variable. Then have problem like calling this medium blur here, so maybe I can make the noise variance bigger so it's more apparent. So like this is 15, I guess it's the standard deviation. So you can see some of this dark pixel here. Why so? Can you guys, do you guys know why I have some dark pixel here?
Because you added noise to the photo.
Yes, and then? No. Yes, I add noise, but if I don't do the next step, it won't have that problem. Because afterward, I convert back to unsigned integer, right? Only have like range of 0 to 255 because it's unsigned integer 8 bits, right? So if my range get up to like 257, something like that, it will just go back to 0 or 1, 2. So therefore, like this, some of this pixel got flip. So yeah, like this. So of course, I guess it's so much fun for filtering. So we have this medium filter, and we say Gaussian filter, and let's see this Gaussian filter again at the result of Gaussian filter. And we also mentioned that bilateral filter. We can also try bilateral filter for this one. So bilateral filter. This argument, I guess you have to verify that they have some of these parameters in bilateral filters. There's a pity. Okay, I guess I do Gaussian filter and bilateral filters. I just bilateral filters alone. For this, it's hard to say. Like I don't know. Which one is good? And of course, you have some parameter to tunes as well. I think this probably is the patch size, and this is some of this to decide like how. I don't know. You need to go to the documentation there. So let's see what else I want to show. Oh yeah, actually near the end we also talk about histogram kind of equalization, right? So let's try that also. So I download one image from Wikipedia that is that basically that image I showed you in the slides last time. Let's see. Let me show that first. So this is the one have the range is pretty not adjust very well. Range of the intensity. So I can compute the histogram using a kind of like cal histogram command in CV2. This is a little bit annoying. So I guess it's like kind of the interface with C. So for some reason they have this artifact here. I need to have this bracket here to make it happy. So this is more or less like I have 256 bins there, and the range is 0 to 256 for that image. And still, I think it's like which channel like I'm looking at. So I have this histogram. I can plot the histogram. Oops. So you see, like it's kind of the range is not good. It's like basically concentrate at like from 120 to 200 something. So I can do an equalization. Does already have a, let's see, I have an equalize command there. So let me just here. Maybe I call it new image again. CV2.equalize histogram, just that. And did I have some error? Let's see. Source is not a numpy array, neither a scalar. Why is that so? Oh, okay. This time I don't need the bracket actually. Oh, I forgot. This the image look like it's grayscale, then therefore I forgot. It's not grayscale image, right? This JPEG like store as like the image itself grayscale just because like this white, green and blue channel, all of them are identical, but it's not a grayscale image. I need to convert that back. Come over here. CV2 color and BGR2 gray. So hopefully you should. I'm missing a bracket here. Oh, yes. Okay, now it's okay. I can do. I can show the image again. It should look much better. Yeah. So that's histogram equalization. Actually, you can look at the histogram again. Let me show the histogram also. Histogram. Let's see. I want to compare histogram again. I'm going to copy this command. What happened?
Maybe got that what?
Yeah. I'm doing pod. Sorry. My brain is not working. Okay. Yeah, it's more like it. So it's just stretch the. But as I said, you are actually not getting more information, right? Because it's just like remapping the color into, the intensity to different value. So okay, I guess that's all I have for kind of a little bit OpenCV. So any questions? So okay, and one thing I really need to do something for logistic. For you guys that taking as a graduate session, so as I mentioned, need to present somehow, right? So what I'm thinking is so spring break is here, so it's 17-19. So I guess we have like we have in total here, I think it's like grad student is 8 in Norman and 3 in Tulsa. So 8 I will need 4 classes. So I'm thinking like maybe like this, like Norman, Tulsa, Norman, something like that. Maybe 2 guys here, like 10, 12 Norman, and then 24, 26 Tulsa, and then these 2 will be like Norman again. So any objection for that? So then I will kind of do a lottery. I will prepare lottery next time. So then just say for the order. So for the kind of like earliest presenter, you're expecting to present like March 10 then. Right? So I will let you know whether like the order next time. So but you won't need to present until at least a month afterward. So that should be sufficient time for you to prepare. Yeah.
How long do you want those presentations to be?
It's about half an hour, and so half an hour. You expect maybe like 5 minutes like for questions, maybe. Yeah.
The presentations will be done through Zoom.
Yes. So when Tulsa, for Tulsa, I guess I will be in Tulsa at that time. So okay, then I may need someone to help me to set it up here. Brandon, can you do that?
Sure.
Yeah. So then like
Half an hour presentation.
yeah, half an hour. So half an hour is a lot, honestly. Once you start kind of like talking, you realize that you can already spend half an hour. I didn't expect that. Like it will take this long, honestly. Yeah. So especially if you try to explain the stuff like clearly, like everyone is hoping everyone is understanding what you're talking about.
So do you have any other requirements for the presentation? Like what you
No, not at all. Only relating to like computer vision. Yeah. So format is totally kind of like open. So you can be even just if you don't want to prepare any slide, that's will be fine also. But then we need to have a camera to shoot the board. If you want to really just use the board, that's fine also. Or if you want to just do a demo, like have something, that's good as well.
Are you saying you're not going to have guidelines for the presentation?
No, I mean, if you want, I can put so-called guideline, but the guideline is like this. All I'm saying, like it has no rule, basically 30 minutes no rule. It just like it has to be relating to computer vision. So I don't know. Isn't that is better this way? Otherwise it's yeah. Of course you can. Okay, if you want to be more canonical, if I want to say use that word, then definitely you can do something like similar to what I do in class. Just prepare some slides, and just have like maybe have a topic you're interested in, dig up a couple papers, and then give an overview of like the whole topic, and then like what was the why people are interested in that, like what's the key problems there, and then like what's the state of the art, and then maybe introduce one tool solution for that. Honestly, that will be much more than like half an hour, but therefore like I don't think you will need to cover all aspects in this way, because it depends on which problems you're talking about. Right? Some of these problems is really intuitive. You don't really need to talk about. For example, I have 3D reconstruction. When you say it, like already people know that what you're talking about, then you can go right away into the technology, right? But some of the problem, like if you're pretty kind of, for example, like specialized, for example, weather application using computer vision, something, maybe even you introducing the problem, you spend like 15 minutes, right? Because like this is something like not everyone know about, and maybe you need some time to just. So I don't think I can give you a really straight. You should spend 5 minutes introduction and stuff like that. It just doesn't fit everyone, I think.
If two people were to come up with the same or a similar topic,
I think it's fine.
Okay.
But I will. I probably ask you guys to try to get the at least the title of the topic, say by mid maybe what we say we have mid-February. Then you guys, if you really have two titles really identical, then you guys can coordinate a bit with.
Maybe we could use the
Yeah.
Piazza.
Yes. You guys can use Piazza to discuss as well.
And we don't have to implement one of the releases.
No.
Just have
It's you can consider this as a general exam kind of like you just talk about that, or the prelim like you can actually have the things done in the final defense, right? so like yes.
You have to pick a problem that hasn't been solved? Is that what?
Oh, no, it doesn't necessarily. Yeah, It doesn't necessarily to be, it hasn't to be solved. But if it's totally, I don't think it's necessary, but it
Throw
cannot
something
be
in mind,
too. I mean, it cannot be something at least I already cover in class, right? That would be like pretty meaningless, right? So, for example, you cannot just go back. Okay, let's talk about filter again. It may not be a good idea, something like this. Yeah. So.
This is just for grad students, right?
Yes, only for grad students. Yeah. Only for students register for the graduate session. Yeah. So some of you, I know you are accelerated programs, so but you register for the graduate session, you're still supposed to do that. Yeah. So okay, I will show you guys the lottery next time then. I'll do the lottery next time. And so what I'm going to do next, I don't know what time, probably I won't finish everything, but I will start to have another kind of like rather introductory topic. Like I like to talk about some frequency. What happened? Okay, so let me start to make you guys a little bit interested first. I just show you a couple like videos that maybe I want you guys to try to explain like what you see in the video. So what's going on? Yes. Okay. Let me show you one more. This is kind of fun. Okay. Let's where is it? This is something I will show you next time. This one. Right.
So would you do like edge detection?
No. It's not actually.
That's not a constant speed.
Look at this one also. Like it's something similar. Okay, it may not be as clear as the last one. It's like at one time it's just going back to the opposite direction. So I guess Mookie gave one answer, but I don't know whether you guys hear his answer. Like, so anyone else has had a comment like why you're seeing that? Why you're seeing that? The helicopter is not, I don't know. I'm not spinning like fire in the sky.
That one's a little too convenient. I think there's some manipulation on that.
Right?
Yeah, that's totally a thing.
The wheel thing on the car, that's normal. You see that every day.
Really? No. Oh, okay. Maybe I don't know. Oh, how about the maybe focus on the helicopter? Yeah.
Is it frame rate?
What?
Like how we see like what in life frames?
Yeah, actually, it's like I guess some of you guys mentioned that because when you look at video, like we always you know how many frames per second like for video, right? Do you know?
But there should be a combination of both. It should be the shutter
What?
speed. It should
Yeah.
be the shutter speed and the frame, like the number of frames that we can see per second. It can't be like one exact. It should be both.
I think it's the shutter.
It's not just
and the rotation of the
yeah.
light.
Actually,
Both things.
I think just the shutter is sufficient to. So but do you know what's the frame rate? Like the typical frame rate? Actually, sorry. What? Video? 24? Yeah. 24? Yeah. So it's around like 24, 30, whatever. So this is another example, like what you're seeing, like think of like you have this wheel, it's like move, I I need to get this again. So think of this wheel is like moving in this direction here, right? It moves in this direction. So it continues to move this direction, but I have this shutter open, so I only capturing frame at this time, this time, this time, this time, so on, right? So if you look if you just look at the video, so what you see will be, if you don't focus at the dot, will be more or less looking at, you will be kind of has an illusion that like the wheel is actually moving in the opposite direction, right? It's like, it's actually, this wheel is turning counterclockwise instead of like turning clockwise. So everyone see that? So it really depends on the sampling. So therefore we are going to talk about frequency today. So of course like this is like for video is like the time frequency, but actually later on I want to focus more in the spatial frequency. It's like you look at an image. So when we talk about frequency, be very careful. When we talk about video and we talk about frequency, there's a couple things here. You can talk about frequency as how many frames per second. I can talk about for each image, there's some spatial frequency for that signal. I can also talk about the light is as a frequency. So I'm mostly talking about the spatial frequency here. So be very careful like what we're talking about here. But before that, like just a reminder, like some of you guys should have this Fourier transform in class, and so it's better review some of this. And Fourier is actually a pretty interesting guy. He has this idea is basically like his main idea is that you have any signal, you can basically decompose into sine waves, because sine waves add them together. So that is Fourier transform. So essentially you have any signal, you have can think of you have two domain here. If a time domain, if I think of a 1D signal here, oh, my handwriting is horrible. I have a time domain and I have a frequency domain, right? Then I have any signal, whatever. I can, okay, this of course is not possible. This is, I'm sorry, this part, ignore that. So I have any signal, have a corresponding frequency representation. So maybe I don't know. Oh, it's horrible. Anyway, but this is 1-to-1. So, and so this is an example. For example, if I think of a step function, kind of repetitive step function, I can continue to decompose that. For example, I can have this add this sine wave. I can have this one here, and then this continue to add more sine wave, become this. If I continue to add that, eventually become this step function. And actually, the idea itself is pretty not received by the big wigs at that time. For example, the famous mathematician at that time were Lagrange, Laplace, Poisson, and so on. All of them didn't think that is a kind of very rigorous idea. So, but it just more or less works. So in the sense that it's mostly true with, of course, some limitation. For example, your power is supposed to be limited, that kind of stuff. Then under those situations, you can have that frequency domain representation. And now back to image. So as I mentioned, so we want, when I talk about frequency, from now on, I'm mostly talking about the spatial frequency. So what do I mean by spatial frequency is that if you look at the image, maybe just in one direction as a signal, then can also have sinusoidal variation, right, the intensity. So this one, if I go basically horizontally, I have a sinusoidal increase and decrease, and vertical doesn't change. So then I will have different frequency, where I can change faster and slower. Okay. So for example, if you look at this guy, actually will correspond to a Fourier representation like this. I'm not sure you can see this carefully. So there's one dot here, and a dot here, and another dot here. So we have a DC component. There's a constant component is non-zero. Then it's a frequency, a slow varying frequency here. So you can see here for this image, So the dots is like farther apart, right? Because it's oscillating more rapidly.
What do the bottom row images represent?
Oh, this is the frequency domain.
Frequency domain.
Yes.
Okay.
Yes. Okay. Yes. I guess I should slow down for this one because we are from 1D to 2D representation, right? For 2D, now your frequency domain representation is also 2D because your original image is 2D. Your corresponding frequency representation will also be 2D. So it's like the Fourier transform is not like it's very nice, right? It's one-to-one correspondence. The number of information, the amount of information in the spatial domain and in the Fourier domain is identical. So if you need so many elements to represent something in the spatial domain, you will need this exact amount of elements to represent in spatial frequency domain. So so therefore original is 2D. The frequency domain will also be 2D.
What does each of the dots represent?
Dot here will be the intensity with the dot is the values there. So therefore, like it's basically like every frequencies I have 0 there, except for these 3 frequencies here. It's not 0. Yeah.
Does the center represent DC?
Yes, the center represents DC. Here it's not very clear. It's actually still have a DC component. So, it has to have a DC component because typically we have an image. It's not represented as 0 mean, right? Because we set an image have an intensity from 0 to 255, right? So there will be a DC component there. So of course this is a little bit like the way how we represent images. If we change our tradition to like say minus 126 to 125, then there will be no DC component. Yeah.
What does the space between each dots represent?
That will be like the frequency, yes. Because that is saying that here, like you don't have any signal between these two dots here, right? Between the DC dot and this dot here. So, or if you think of this from this image, or like for this image here, you have a dot closer to this DC component. That means that you have a slower varying AC component there, right? And in this image, you don't have that. Therefore, it's totally dark for those frequencies. And then only for there, you have one dot there. So any other question? So then if I have oscillation, for example, if I have this flip by 90 degrees, so what do I expect? If I have like this instead, it's hard to draw. I hope you understand what I mean, right? Yes, the dots will become vertical. We have 3 dots, 3 vertical dots instead here. So therefore, you can also see if I have like diagonal, kind of like, what do we call like parallel lines there, then therefore I will have like these 3 diagonal dots here.
What if you had like concentric circles?
Concentric circle, that will be, it's actually will be, you will have like something like concentric circle also somehow because you're expecting component everywhere, right? But you won't get dots. Will be like more like pattern. Yeah. Actually, if you're interested, I have demo here, but you need to find a concentric circle for me to shoot that. Yeah.
I don't think what we're doing here is frequencies at all. Because I feel like we're missing out on a lot of other colors in between. So I feel like we should go to like a logarithmic scale.
Oh, wait. That's what I'm saying. Like, when we talk about this image video, be very careful because there's frequencies I overload word. Yeah, it's a spatial frequency here. So I have nothing to do with color here. So here it's just intensity. I look at intensity as a signal, so it's just a signal. Think of this as a signal. It's a 2D signal. A 2D signal, how it's varying, therefore you can have a frequency, you can describe frequency. Just like in 1D, you have a varying signal, you can talk about frequency for that. But now here you extend one more dimension, so you have a 2D signal here, so you have a more complicated two-dimensional frequencies. Yeah. Yeah, it's a little bit weird first. Yeah, but your two-dimensional frequency will be like you. Maybe if I show more example, it will be like, for example, like this is another example that I can actually add these images, two images together, then you can get the effect of like, now I have like 5 dots here, right? So I have both like some diagonal frequencies here and some horizontal frequency here, so I have this added them together. So any other questions, comments? So just like in 1D case where you have Fourier transform, basically every 1D signal more or less you can represent as like summation of like different sinusoidal signal, right? So you can also have bases like this is a kind of like patches like varying in different kind of like frequency, different angles, and you can think of like any images can be just combination of those, just like weighted sum of all these different patches. And of course, if you remember Fourier transform, actually, it's like you have a cosine and sine component, right? Because it's like f. If you just a reminder, your Fourier transform in 1D, or actually I can even write 2D, right? 2D would be something like I have a frequency. Sorry, not frequency. I have a signal. Maybe I shouldn't use f, but I already write f here. But anyway, so this is like basically the intensity of the image. Think of. So then the Fourier transform will be something like that, right? EIX. What do I use? KX, I say. Sorry. Maybe I should write like. It's a little bit ugly. So this is the I here. This is the square root -1 here. This is xkx, yky. Kx is like the frequency in the x component. Ky is the frequency in the y component. And then you take the integral or take the summation there over x and y. So therefore, like that, you have a cosine component. This is EI something, right? So I have actually a cosine component and a sine component, like cosine xkx plus yky. Sorry, it's like k subscript x here plus I sine xkx plus yky. So there should be like the cosine patches and sine patches. Here is showing the cosine and the sine patches. Yeah. And this is more example, like, so any images can be kind of reconstruction using this way. So therefore, like if I decompose this image into different Fourier bases that I just mentioned. So for example, if I first basis, I get the first 4 bases, I get this, and so on and so forth. If I get first 400, I get more or less this like this one. And this is a more complicated example, like if an image, what is the Fourier domain kind of representation there? So as I said, it's not easy to figure out honestly. So there's a demo like on YouTube, but I guess I will show you the let's see. I think I have a demo here actually also. So oops, let's see. Camera. I don't know why it's using the camera. Oh, that's a little bit annoying actually. Can I not share that camera? Also, actually, you guys are seeing me in the camera?
No, you don't see camera also.
Yeah, somehow it's using the camera. Let's see. Let's see if I can. Yeah, or I need to change this code here with a webcam, but it uses a video. It doesn't use the standard. Okay, self-capture cam device. Let's see, cam device is what? Cam device. Or default, maybe set the default to 1. I guess that may work. I need the webcam here. So hopefully this works. Oh yeah, this works. So I need something to look at, but you see, like, let's see what kind of pattern is good. So maybe I try something loving, then maybe it's more like this is oh, actually this may be good. If I'm able to draw something, then maybe I can.
Yeah, the concentric circles are going to be like
historical as well.
very marked.
Let's see.
Camera auto adjust to light intensity.
I guess a little bit, probably. Let's see. Let me see if I can. Wow, this is difficult. It's too dark. It's too dark. I don't think you can see it.
Oh, I see something.
Yeah, it's not making concentric circles, but very thin.
If you guys are interested in circle, I can make circle.
It's getting reflection on your.
Yeah, this is a little bit difficult.
We can do it on the.
Oh, okay, that's a little bit better. Yeah.
Can you like draw another circle around it so we can see that?
Inside, outside, I'm not sure. Like,
Doesn't matter.
okay, I make inside maybe.
Yeah, it's not even concentric circles. Do you see them?
I see you. There you go.
Yeah. Can move around. So if I more or less in the. Yeah. So what else you want to see?
So how, if you translate the camera like up, down, left, right, how do we see?
Yeah,
that?
I guess you mean the circle is like if it's in different paces, right?
Yeah. What change do we see in the frequency domain?
So, in the frequency domain, what you're gonna see is like the most prominent color you are seeing in your, or like the most prominent frequency you are seeing in your picture. So it doesn't matter where your circle is. If you have a lot of black circles,
But the information should be there somewhere, right?
Yeah.
no, you're just like seeing like how many components you have for each frequency. You're not seeing a lot of information. You're just seeing.
You should be able to reconstruct it, right? From
Not
Yes.
completely, not fully.
Yeah, this is definitely quite confusing. I guess I have the code there. You guys can play with that. And another thing like here, maybe I need to give a remark because the circle is a black circle. I'm not having a dark background. I have a white circle here, so the signal maybe is flipped. I don't know. I don't know how you process it. Actually, I'm not quite
Can you like look up in Google like concentric circles pictures and show it to the camera?
concentric circle. Yeah, I can. Actually, let's see. Concentric circle. This is
Yeah,
a,
like the last one on the right.
yeah, like this one?
Yeah, there is
Okay.
parent.
This one is very nice. So I can go closer, then I
Maybe
guess
show one quadrant of this.
one quadrant of that
If you can.
is a little bit difficult.
Yeah. Okay.
That's not the infrared and left.
Yeah.
It's just the
You want to make it upper left or right?
Yeah.
This is upper right.
Okay.
It's difficult. Yeah, there's some of these something above the capture this some of this also.
What if you do the top half?
Top half. Let's see.
It's missing sections of
Yeah.
the circle.
I think the sections missing are because of the white strip, like in the other column. It's not because they're not like.
Okay, I guess I. But you guys can play with it yourself, like at home. So
Do you have the code somewhere we can?
yeah, I have the code here. Actually, I have the code.
On the website?
Yeah, that's on the slide there. But it's basically his code. I
Oh.
just made very few changes. I made the changes because it didn't have like, it didn't end gracefully. It didn't have like a pass queue to quit. I just add that one. Let's see, did I quit that already? I forgot. I guess it's okay. So anyway. Okay. So here is some exercise for you guys, just to guess. So which is which?
I think number 3 is A.
Yeah, I think so too. Yes. That one is probably the easiest to guess. And then which one?
1 and B.
And then D. Yeah, probably. The other 3 is like difficult. Yeah.
I would say
4 and B.
4 and B.
4
5
and B.
is C. And 5, no, 5 is C. I think it's 5 and B.
I think 2 is B because B has the most color variation. And that's a wider circle, maybe. And then 4 maybe E because it's picking up on those pillars of rocks.
Mm-hmm.
And then 5 is C because there's lots of horizontal lines.
Oh, okay. I think you're probably correct. Actually, I think 5 is C also because we see this is tilted. Like this one is tilted, C is tilted, and also 5 is tilted. Yeah. So yeah, I think he's basically right. Oh, correct. Wow. Cool.
We did that.
Image processing?
Yeah.
Yeah. Okay. Yeah. So what else? Oh, Fourier transform. Of course, I mentioned the sine and cosine component. So because the sine and cosine component, you can also represent that in amplitude and also phase, right? So I can also like, instead of looking at cosine and sine component, I can also split into the amplitude and phase image. Actually, here I show what I showed earlier on is always showing just the amplitude or the magnitude. But if you look at the phase image, it's actually even more, I don't know. I don't think like anyone can get much from the face image. That's a comment I got like, from a professor in University of New Mexico. You can read it yourself. So, so I basically like I don't believe anyone can from the face and figure out what image is which image. But very interestingly, like before you leave, like just one thing, like just one last thing. Basically what I did here is two images. One, I am showing the face of the zebra, and then what's the other animal? I forgot. Cheetah or like, oh yeah. Then there's a face of the zebra and then the amplitude of a cheetah. The other one is just vice versa. So which is which? What do you think? The left one here, let's say. Left one, the face is like the face of a zebra or face of a cheetah?
Cheetah. But the face is cheetah.
Face cheetah? How many, okay. Take a vote, this is interesting. Face, anyone think it's like face of a cheetah? So, or therefore amplitude of a zebra. So how many, hold hands. Yeah, okay, I think majority. The West? So the West is just the other way around. So other one, you need to hold hand as well. Face of zebra and amplitude of cheetah. Hold hand. No, it's for you hold for both actually.
I think it's the amplitude of the zebra and the face of the cheetah.
Amplitude of zebra, face of cheetah.
Yeah.
Yes. I thought that was the first option. Is that the first option? Okay. Let's redo again. Then we'll go. Redo again. Amplitude of what is the first option again? I'm sorry. I don't know.
Amplitude of cheetah face of zebra. No, that's the second option.
Okay. I only say amplitude. Okay. How many think this is amplitude of zebra? Amplitude of zebra. Okay. The other one, amplitude of cheetah. So that means the other one think that this is face of cheetah, right? Okay. The answer is. Well, I don't know. I guess wrong also, honestly. I mean, I think this would be like the amplitude of the zebra because it looks like if you look at the amplitude image, you can guess more stuff, right? But it turns out it's not. Actually, those face images very hard to interpret. Somehow we interpret that like with our brain somehow. So yeah, I don't have an answer for that, but it's just worked this way. Maybe you can study this also as your final project if you're interested. I don't know. Maybe you can take it up. Maybe someone did that. And just final remark, like this is very interesting because you think of that for audio perception, frequency is important. Phase is not important at all. We don't care about the phase. We only care about the frequency when we listen to sound. So this is not a must that one way is more important than the other. So I guess I will just end here. Like then we'll see you guys next week.
Well, if you own noise canceling headphones, I think otherwise.
I don't know. Yeah, that is count. That will count, but.